So I'm Joe Rad. I'll present to you today our approach of detecting erroneous identity links in the web of data. As we all know, identity is an essential thing for linked open data, essential ingredient. It allows to link different IRIs, link IRIs from different data sets, and consequently linking these data sets. This is done usually by linking two things that refer to the same entity by an all same as statement. This statement means that every property asserted to the first IRI will be asserted to the other. I'm talking about all same as because it's the most adopted identity statement in the LOD. As we can see, it's sparkly adoption in the LOD cloud in 2015 compared to the other identity and near identity links. However, from all these 500 million same as statements, there exists a number of erroneous identity links. And there has been studies that have proven that all same as is being used incorrectly in the web. This is due to the lack of precision, maybe not 100% precision, of data linking approaches. In addition, people tend to use all same as because it's the closest formalized identity predicate that can be used. For example, because sometimes you don't need to make an all same as link, but since it's the only available standardized identity link, people tend to use it sometimes incorrectly. In addition, two IRIs that are linked to each other, sometimes these IRIs' meaning tend to change by time. For example, thing referring to a person now might refer to the web page of that person. And finally, the notion of identity in itself is problematic. As in philosophy, many critics have been made against this notion of identity, which is standardized in all same as. This same as problem is obvious in the LOD cloud. As we calculated the equivalence closure of the all same as statements, and in one equality set, which means that 177 terms are actually linked by same as transitively and should refer to the same real-world entity, actually what we have is a bunch of terms which do not refer to the same real-world entity, like the list of countries, Albert Einstein, and many other different things. So this is obvious that all same as is being used incorrectly in the web, and we need to detect these wrong same as links. How can we detect these wrong same as links? Many approaches have been already tried to detect these links. Some of them have been based on inconsistency approaches. For example, they hypothesize that links that cause inconsistency are probably incorrect. Other type of approaches have relied on the content of the IRIs. So, for example, they are comparing the textual descriptions and the properties of these two IRIs in order to see if this is a correct same as link or not. And finally, the other type of approaches have relied on the network structure. For example, they study the effect of an all same as statement to the Rdf graph. For example, an all same as statement which enriches the other IRI is probably more correct, and an all same as statement which tend to close an open same as chain could also be probably correct. So we have these kind of approaches that aim to detect the wrong identity links. What we need from such approaches is to have obviously high accuracy, recall, and precision. We want them to be tested on real-world data. We want them to be scalable to the web. And we don't need assumptions that cannot be available in the LOD, in the web. For example, many approaches have relied that each IRI has a textual description, which is not the case in the LOD, for example, or the presence of schema mappings, which is also rarely the case. So, for example, we find ourselves with no existing approach that can combine all these criteria to detect the wrong same as links. And that's why today we're going to introduce you our approach that takes in consideration some of these criteria necessary for detecting the wrong same as links. Overall idea of our approach is that we want to use the community structure of the all same as networks to assign another degree to each same as link. What we hypothesize is that terms that are densely connected to each other are probably the same as links between them is probably correct, while a term that is an outlier, like not connected to the other terms, is probably connected by a wrong same as link. In addition, we take in consideration the symmetrical property of our same as link, and we consider that our same as link, which is duplicate symmetrical links, are probably more correct than our same as link, which are not symmetrically asserted. I present you our approach, which is composed of 4 main steps. But before, I'm just going to say that we have used the lot data set that contains 28 billion triples. And the first step of our approach necessitates extracting the same as statements from this data set, obviously. So when we extracted the same as statement, we have now 558 million statements. From this network of same as statement, we want to detect the equality set. An equality set is just a connected component, meaning that things in the same equality set should refer to the same thing. An example of an equality set is the Barack Obama equality set. For example, in the LOD cloud in 2015, Barack Obama has 440 identifiers that should refer to the same thing, which is Barack Obama, linked by many same as links. So this is one equality set. After that, we have detected the 49 million equality sets existing in the LOD. We want to detect the community structure in each equality set. There exist many algorithms to detect such community structure, and we have used the Louvain algorithm because we want to detect non-overlapping communities. We want an algorithm that can consider the weight of the edges. We also want an algorithm that has low computational complexity, and because the Louvain algorithm has proven its efficiency according to the other survey in this domain. So now we have the same as network, which are composed to a different equality set, and after we apply the community detection algorithm on each equality set, now we want to assign an error degree to each same as link in each equality set. As I said before, our error degree is based mainly on 2 things: the density of the community in which our same as link exists in, and if this same as link is symmetrical or not. So the idea is, as I said, terms that are very connected to each other, a same as link between them is probably more correct than a term that is not connected to the rest of the terms. Therefore, with this hypothesis, we assign an error degree between 0 and 1. And as I said, also we consider the symmetrical characteristic. For example, on the Barack Obama equality set of 440 terms, we can detect this community structure composed of 4 communities. What's interesting about this community is we see that the community 0, community 3, and community 2, the IRIs in these communities mostly refer to the person of Barack Obama. While in the community 2, most of the IRIs actually refer to the government and the administration of Barack Obama. So this is also obvious that same as link, same as is used incorrectly, and this is also a proof. So what we need, for example, is to detect the links that is causing the linkage between the person and the administration. So now that we have assigned an error degree to each same as link, we have here the distribution of this error degree on the 556 million, because we're not counting the reflexive ones, because by definition, a null same as, which is reflexive, is correct. So the objective of our evaluation is to check if our error degree actually assigns a higher error degree to wrong links than the correct links. And the second objective of our approach is to investigate which criteria are actually affecting this error degree. So to do that, we have asked the authors of this paper to manually evaluate 200 same as links from each bin of the bins that I've showed you before. So for example, authors have evaluated 40 links with an error degree from 0 to 0.2 and etc. So from this table, we can see, the first result is that the higher an error degree is, the more likely it is that the link is the more likely a null same as link is erroneous. For example, we can see that from 0 to 0.2, all the same as links evaluated were actually judged as correct same as, while same as links with an error degree from 0.8 to 1, 68% of them were only correct. So we can see that our error degree tend to give higher error degree to wrong same as links than to correct ones. So that's the first result we can see from that table. The second result, we can see that all the same as links with an error degree less than 0.4 are actually correct, judged by the authors of this paper. But what we cannot deduce from this table is which error degree and which is the threshold of the error degree in which the links start to be incorrect. So because we have here like 31% of them which are incorrect, in order to investigate more, this bin actually, we have evaluated 60 more links. But this time, we have taken same as links with an error degree higher than 0.9 and with 3 other different criteria. The first criteria is we took 20 same as links with an error degree higher than 0.9 in the largest equality set. The second criteria is that we took 20 random same as links with an error degree higher than 0.99. And the third criteria is we combined both by taking an error degree which is higher than 0.99 from the largest equality set. So from this table, we can see that actually our error degree works better in larger equality sets and when we set the threshold at 0.99. For example, we can see that in this criteria, 88% of the links evaluated in the largest equality set with an error degree higher than 0.99 were actually incorrect. So that means that the size of the equality set can impact massively the distribution of the error degree. However, and since the equality set size is not included in our error degree, we took only the threshold as 0.99. And we, by looking at the links we have evaluated in this approach, we can see that we have an 86% accuracy from the links we evaluated. So we assigned, so the links that are lower than 0.99 were actually correct, and links that are higher than 0.99 are actually incorrect with an 86% accuracy. The precision is 73%, and which is also according to the links that we evaluated. However, randomly, we also, because we saw in the other criteria here, randomly, if we took links that are higher than 0.99, actually the precision tends to be more than to 40%. So we can see that the precision depends heavily on the equality set in which this link is taken from. To evaluate our approach on other identity links that we took, we relied on the only gold standard we have seen in the LOD, which is that done by Acosta et al. From crowdsourcing. They have actually took 95 same as link connecting Wikipedia to Freebase. They manually evaluated them, and they've seen that all these links are actually correct. So we wanted to see these actually correct links, what kind of error degree they have in our approach. We managed to find only 78 in our data set. From these 78, 77 were assigned an error degree lower than 0.99, which shows an accuracy of 98% in validating identity links at least. In order to evaluate the recall of our approach, we have chosen 40 random different terms, like Facebook, strawberry, chair. We just took 40 random terms that are not the same. We made sure that they are not asserted same as in the LOD, but we also made sure that some of them are actually in the same equality set by mistake, which is erroneously in the same equality set. And we added all the possible 780 links between these 40 terms, and we have seen that 725 of them have actually an error degree higher than 0.99, which shows that we actually managed to assign 93% of these wrong same as link that we added as a higher than the threshold we set, which is higher than 0.99, which shows a 93% recall. So in order to finalize my presentation, I'm going to come back to the equality set of the Barack Obama. And we saw that the government community is connected to the rest of the terms of the other communities by only 2 links, which are here. This link is actually a free-based, this IRI is actually a free-based IRI connecting to 2 DBpedia IRIs, which is by these 2 links. We looked at this free-based IRI, and we saw that this free-based IRI is actually the presidency of Barack Obama, linked to President Barack Obama and President Obama. So we looked at these 2 links, what is the error degree of them, and we saw that we have actually managed to assign an error degree that is 0.999, which are the only 2 links in this equality set with this kind of error degree. So we can see that it was effective also in this equality set of size 440, for example. So now to order and finalize my talk, we want to just look how much messed up is the LOD, how many incorrect same as links are in the LOD. So we also did other analysis that are not included in this paper about the symmetry of same as. We have seen that 98% of symmetrical same as links tend to be correct. And we took this in consideration with the number of same as links which have higher than 0.99 error degree. And we can estimate that 4% of all same as links in the LOD are actually erroneous, which means around 22 million same as links. This estimation falls in line with Hogan et al. Estimation in 2012 and is much more optimistic than the estimation of Halpin et al. In 2010 also, which said that 21% of all same as links are incorrect. So in this talk, we present to you an approach to detect erroneous identity links using the same as network structure, network community structure. Our approach do not require any assumption on the data like the previous approaches in state of the art, so which makes it feasible on the web. And with a total runtime of 11 hours in total to extract the same as links and detect the connected component and assign an error degree, makes it very scalable to the web. With an accuracy of 86% and recall of 93%, we have shown some good results on this evaluated set of links that we manually evaluated. However, we have seen that the precision of our approach depends heavily on the equality set size, and clearly an equality set size of size 2, for example, our approach will not be effective because we cannot detect a community structure in such a small equality set. And all the numbers that I'm showing you are actually based on the manual evaluation of around only 300 same as links. So as perspective, we can just include the duplicate same as triples. We can see if we can include this equality set size. We can combine multiple community detection algorithms, combine with other state-of-the-art approaches, and maybe replace these erroneous same as links with contextual identity links. Thank you.
Much about using graph embeddings and what would be some of the limitations to think about unsupervised clustering of graph embeddings to do this?
No, we haven't thought about this for now. Actually, there's another approach which relies on the vectors of IRIs. So it constructs a vector which is done by Heiko Pollheim. And so that's the closest to machine learning maybe approach to detect wrong same as links. But actually, we only relied on the community structure and the density of the communities and the symmetrical of the same as links at the moment. But we can check this as a perspective. Thank you.
Time for one more question. I have a question too.
Yeah.
If you combine the content-based approaches with the network approaches, do you think you will be able to?
Yes, actually, what's good in our approach, for example, we can pass in the beginning because we're scalable in the web, so we can assign an error degree to each same as link before and give maybe the same as links which have a higher error degree to other type of approaches which do not scale to the web, like content-based or maybe crowdsourcing or some other approaches to verify and improve our precision. Thank you. You want some?
Can I have some mic? Right. Thanks. Welcome. Getting the most out of Wiki Data. So let's talk about hurricanes. So yesterday, I was inspired by the keynotes, not just regarding privacy, but also I wondered, isn't it awfully common these days that we get these hurricanes and have to cancel talks or whatever else because of that? Sorry for the connection problems. So I went to my computer and asked, so computer, can you show me a timeline of tropic cyclones through history so I can see that happening? And a few seconds later, my computer showed me that timeline of tropical cyclones. But I noticed that this is a bit dense at the present end, so it wasn't really very useful. And I said, okay, can you please aggregate that so I see the number of cyclones per year? And here's the result I got. Well, it seems that there's a bit of an increase recently. We may have to look at this as well as humanity, right? But of course, this kind of interaction with my computer is not really what happened, right? This is the kind of science fiction thing that you may write into some visionary paper and then hope you can inspire some people to work on it so that maybe 10 or 20 years later, something in that direction is actually possible. Now, thankfully, 16 years ago or so, 17, some people wrote such a visionary paper and they inspired a lot of people here and in our community, including Danny Fernandez, myself, and many others who were affiliated with Wiki Data or with Wikipedia at the time, and inspired us to look into how one could actually make information like this accessible at your fingertips. I mean, admittedly, we still have to do more on the natural language side to really have the interaction, but I could say we now have the backend in 2018 for some of this type of functionality. So this backend largely, for the purposes of this talk at least, and for the queries that I just showed you, is Wiki Data, which you have heard about, I'm sure, which is a wiki-based knowledge graph where you have a MySQL backend relational database set up in a normal web application way like many other sites, just at a somewhat larger scale. On the other hand, in order to be able to ask such questions, you need to have some kind of approach, some kind of declarative, versatile way of phrasing your information need. And thankfully for this these days, we have Sparkle, and we also have systems that can handle Sparkle in an interactive fashion to answer such questions quickly. In our case, this is BlazeGraph. And then if you have two such things and you want to exchange information between, what you also need is to some kind of interchange format that allows you to transfer data back and forth, and possibly to do that in a live way so you have current data. And this is, of course, RDF in our case. So this is how semantic technologies work together now at Wikimedia to power the Wiki Data Sparkle endpoint. And of course, you cannot just ask about hurricanes, but about many other things. For example, here's this nice query of where people are born who travel to space, color-coded by gender, something that you can bring up very quickly. Or if you are looking for 19th century paintings of the moon, then this is what you can get again through this endpoint. Of course, the visual displays are something added on top. It's not plain Sparkle results you see here, but it's not hard to get that. And you can even do more complicated aggregated things like asking for which days of the week disasters occur on. So this is an interesting one. It turns out Friday 13th is not particularly dangerous, and Thursday the 11th neither. But we have to watch out for certain Mondays and Tuesdays, really. But I think these are not next week. Okay, so this kind of aggregates you can do, and if you know Sparkle, you will already see that it might be a bit challenging to get such a thing out of Sparkle, but people manage, right? Now, should I say something about Wiki Data? Well, I think you've seen most of you have seen something of it, right? So it's a large knowledge graph of Wikipedia and other sites in the Wikimedia universe. It has currently about 50 million entities, 570 million statements, and a lot of other information, including labels and descriptions, which are very useful for some applications. And also it has links to all Wikipedias and all other sites in Wikimedia, which is very useful to do information integration, for example. But its true asset, of course, is that it has a community which is relatively large. So it has 230,000 logged-in editors who have made contributions so far. So these are people who first created an account. You can, of course, also just edit without that. And there's now about 18,000 people per month doing at least one edit. So this is definitely a strong indication that the site is in active use, and that's a big success for us, of course. Now, if you go to the site, you will see something like this. So individual pages have a title. Internally, or also for many external purposes, these things are identified by QIDs. For example, Tim Berners-Lee has QID 80, but you will usually see the labels if you're in an application. And on this page, you will then find statements like that. Tim Berners-Lee, place of birth is London. And this, of course, to us looks very much like a triple, and is a thing we readily understand and can work with. And indeed, Wiki Data was very much inspired, of course, by semantic web ideas and efforts when we designed it initially, which is no coincidence. And one such inspiration you can see in the fact that it's very property-centric. So properties have their own identity, and you can assign any property to anything you want to give that property to with a certain statement. So there's no type-based hierarchy or something, but it's a property-based system, very much like Rdf is, for example. But if you scroll further down the page, you will also see statements like this, which among the many awards that Tim received, you will have the Queen Elizabeth Prize for Engineering, which you learn here he received in 2013 together with 4 other people. And these additional pieces of information here is something that you don't normally have in Rdf, right? So it's something we add. It's called qualifiers in Wiki Data, and a colleague recently mentioned the term dangly bits as a suggestion for these small things here, which I find kind of cute. I hope nobody finds it offensive. So these little dangly bits, they have to somehow be accommodated if we want to work with the data. And in some cases, they are really important. In some cases, they are just some background information, but they usually provide context. Now, if you want to do this in Rdf, then of course, the starting point is pretty clear. You have identity provided by the IDs, and you have labels given to all of these things, and usually labels in many languages are available. And now you would like to express that Tim Berners-Lee has won this award. But you cannot directly make a connection, because then you have no place for the annotations, for the qualifiers. And so what we do is what we would normally do. We have an intermediate node here, which represents a statement as such, and it's linked from Tim and to the prize using the property that encodes award received. So P166 is the code in Wikidata for award received, and these are 2 different URLs built on top of this. Right, and once you have that, you can easily attach any kind of information you want, like the people he won the award with or the time that this award was won, to this additional node. Right, so this does work. Of course, it looks a bit complicated, and you may wonder now, how can I, if I have such a complicated schema, won't all the queries also become complicated? And indeed, this would be the case. But Rdf allows us to do something very nice and simple here. We can, in addition to all this structure, also have a triple which directly links Tim to the prize. This has a slightly different URI here. It's P166 again, but with another prefix, so there's no confusion. And now if you are in a situation where you just don't care about extra information, you can just look at these properties and use a query with that. And if you're in a situation where you want to go into detail, you can use the more complicated structure. And the nice thing in Sparkle and in Rdf is you can combine the 2, right? So you can have one query which mostly uses simple things, but for some cases uses complicated things. Okay, so based on this idea, Wiki Data provides Rdf exports that you can get. Every week there's 6.2 billion and growing triples being exported. Currently, it's a bit of a sizable thing in gzip. There's also bzip2, which is a bit smaller. And there are also linked data exports. Of course, all the URIs content negotiate, but you can also, if you're in a browser and don't have content negotiation, just directly open the URI and get the Rdf for one particular entity as it is live on the site. So we are pretty well integrated with the linked data web. And based on this, then the Sparkle query service is established. So this has been actually up since 2015, first in beta mode and now pretty much as an established part of infrastructure. It has all the data, so it doesn't actually use any projection or some subset, but it uses the whole set of triples. It's live. Latency is usually below 60 seconds, often much lower. When you make an edit, you pretty much instantaneously can expect the result to be taken into account. There are almost no limits, actually, also compared to other live endpoints that you may have seen. So, for example, the timeout is 60 seconds, which is pretty liberal. There is absolutely no limit on result size within the timeout. So this is, I think, a new thought that some people have to get used to. You can actually use Sparkle to get data exports. So if you want to get just, a few million triples, you don't have to download the whole dump and filter them out. You can just pose a Sparkle query and you have a few million triples. So there's definitely, in this order of magnitude, it's still possible to just get it live. And this is, I think, a very strong point that one can make use of. Also, you can have a lot of parallel queries. There's some CPU time limit if you really go parallel, but it's quite fair, I think. And there are some extra services. I'm not going to go into detail, but you can imagine there's some demand for geographic proximity in such a service. There's a demand for connecting to Wikipedia APIs to do text search, for example. And it's the nice thing about Sparkle is that through service with some amount of hacking, of course, but still in a fairly standard compliant way, you can use Sparkle to integrate such data sources in a joint form. So Sparkle is a very powerful thing here to use. Right. So how does that look? So if you go to this query URL, which I have on my slides, then you would see maybe something like this is an interface. So you would be able to have a nice user-friendly, somewhat user-friendly Sparkle input editor here with auto-completion. So you don't have to remember all these strange numbers. You can just type the name of the thing in your language and it will find you the right entity. And then you can phrase, for example, this query, which would ask for lines that are part of the New York City subway and stations part of that line and their coordinates and images, and you want to see that as a map, which is a little bit toying around with displays, and then you would get something like this. New York subway is quite big and a bit confusing, but I hope you can see that it's still looking kind of nice. So this is a very simple query, and you can imagine that users are quite excited when they see that with writing just 5 lines or so, you can bring up such a map or whatever else you want to do. And it's really empowering communities by doing such things. In fact, the community is so empowered and so excited that they are doing much more complicated things as well. For example, this query here is asking for films that star more than one future head of government. So you're interested in films where at least 2 actors are people who later assumed leading political positions in their career. And you can see that this is not so easy to formulate, even if you know Sparkle. Okay, so the typical thing that people say is, yeah, semantic web is nice, but you know the problem with it is that. And then there's a string of things, and the problem with it, usually that first people come up with is to say it's too complicated. And I would really say, after having seen this for 3 years in the production use and with a community that hasn't known RDF and Sparkle before, I would definitely say, no, it's not too complicated, really not. I mean, Sparkle is widely used now. We have more than 100 million queries per month to the service. It's mostly an API, so most users won't see it, right? JSON is also complicated. Everything you use as an API is complicated, but these people are web developers. They do complicated things. So for them, Sparkle is just a small thing. If you do JavaScript these days, it's much more complicated. And also the community, even for those who are more like on the data journalist side, who want to do one-off queries for interesting things like hurricanes. The community offers a lot of tutorials and workshops and even online services like this nice page, request a query, where you can describe what you want and somebody will help you to phrase it. So it's really, there are a lot of entry points for people and much more than our community, I think, has created from an academic point of view, because this is now really used. Now, the other problem with the semantic web, right, we all know, is that it does not scale, right? It's a nice idea, but it doesn't scale up. Of course, this is also not true according to our experience. We have BlazeGraph, which scales pretty well. In fact, I was very much surprised by the excellent performance that we got. I mean, this is largely due to Stas, who is here in the audience, and other people at the Wikimedia Foundation who run the operational side of it. We didn't have any outage of the server since it was launched, right? It was never down. The latency is very small, usually less than 40 milliseconds for most of the queries. Still, even 99% of queries answer in less than 40 seconds. There's hardly any timeouts. So less than 0.05% of queries time out. And that's, I think, an excellent thing. It's not that something we can completely be satisfied with. We would like to also go further for this remaining bit, because these are interesting queries. But it shows that you can do quite a lot. Now you might say this is probably a large data center used here, but this is also not the case. So the setup is based on 3 commodity servers with powerful, well-equipped, right, but not supercomputers, using SSD drives, and there are 3 more for geo-redundancy, which are not so much used for load. So otherwise, setup is pretty standard. Linux load balancing and caching facilities as you would use for any web application and company. Okay, right. All of this is also open source and free, of course. This being Wikimedia, everything is open source, and you can also set up your own system in this way if you want to do that. There's all the scripts, all the live synchronization things, everything's open source. In fact, now these days, you even can get Docker images where you have ready-made installations of Wikibase, the whole Wiki Data software, plus the Sparkle store, plus the live synchronization. So you can just directly start using your own database, and it will give you your live Sparkle endpoint in Docker ready to use. Okay, so one interesting question with all of this practical usage is, of course, what are these 100 millions of queries? And we've looked at some of them, like some 500 millions of them in 24 weeks of recording, and it was turning out to be very hard. So actually, from a research perspective, I have to say, we don't really know how to understand large amounts of Sparkle queries these days. So the problem is that there's an extreme influence of scripts and bots. Somebody somewhere in the world writes a script, and suddenly your characteristics of the load are completely different. And this is not somehow averaging out. We thought so at first. We would hope that somehow overall it's still balanced. No, it's not. You will have even over months and years, even we work with this data, there's absolutely no clear trends in this. So things change from month to month. And that's, of course, a bit frustrating when you want to learn something from this. What we did in order to make it more usable is we tried to classify major sources so we could eliminate this kind of error and isolate what we considered organic traffic, or traffic which is really caused by user interaction by people who want to know something. We did that. The methodology for this is in the paper, and the insights gotten from that is that, well, robotic traffic dominates. I mean, 3 bots, in fact, dominate with 60% of all those queries. So it's a huge amount of traffic coming from just 3 sources. But behind these 3 sources are many hundreds of users who use these services. Organic is much smaller. Robotic is mostly data integration and download. Organic are browsers, mobile apps on phones, whatever, miscellaneous things. And the robotic is much more uniform and shorter, whereas the organic is more interesting in many places. For both cases, we found that, interestingly, path queries are very important, which I think suggests that the view as a knowledge graph where you want to reach things is appropriate. And secondly, we also found that these reified statements where you have the auxiliary node and really want to go into detail are used not so infrequently. So 10% of the queries in some of the intervals are using complex statements. Okay, but you can see for yourself, we have actually managed to release all the data. That's not written down in the paper yet because it was a long process because of privacy concerns, obviously. So you can now get all the data, or well, part of it. We will have more soon, hopefully, online to do analysis yourself if you have any ideas how to do it better. Okay, so we hope that this is a useful resource also for this community. Okay, so concluding, semantic web technology, it works. Let's accept that some things are really working out of the stuff we've done in the last 15, 20 years in this community. Interactive analytics and query is affordable for dynamic knowledge graphs with billions of edges. And it's also usable for large communities who are not academics, right? So what we need definitely is more applications, more research, people who do exciting stuff with it, and I think you are in the position to do that. So I have a slide of many thanks because many people are involved here, not just the people who are authors of that paper, to make this possible. And in the end, I think all of you who have made the standards that we are based on, who have made the software that we are based on, should be thanked here for this, I think, big use case and big achievement for our community. Thank you very much.
Query service is really great. I mean, and I say that very seldom if you know me.
Yeah.
Shouldn't laugh. But I don't think you described the query that you showed us correctly.
Sorry?
You showed us a query a little while ago in this presentation. I don't think you described it correctly.
Which one was it?
Because you said a human, and it didn't use a subclass of to look for humans.
A human? Oh.
Yeah, you asked, the query was, find me something that belongs to some category and something else belongs to a different category, and you used the subclass subtype correctly on one side but not on the other side.
Oh, right.
And that's a big danger here, and that is why I would take some issue that this is semantic. This is not particularly semantic because it doesn't correspond to our intuitions as to what's really going on underneath. Oh. It's really just a query against the data.
Yeah, I know what you mean. So I think what Peter is saying is that you have to hardwire the conceptual assumption so that every query is 100% correct. I think to some extent this can be attempted. I don't think it can really be achieved because you will have to know your model. For example, in this particular case, you have to know that every human is a direct instance of human on Wiki Data. So it's this is something that is a kind of a design guideline people have somehow agreed on, right? So it's something that is special about the system. And if you don't know the data, you may think that you have to navigate a large hierarchy of classes to find all the humans, but it's in fact not really the case. But yeah.
Mine is pretty quick, actually. So thanks for the talk. I was just wondering whether you can say who are the 3 bots that you mentioned?
Yeah, so these are data integration. 2 of them are run by Magnus Manske for data integration. So it's basically the data donation pipeline. So people, when they donate data, there is a bot checking whether the data is already there and tries to find matches. And this is a lot of queries. And the other one also was data integration, but from the protein world. That's the second most frequent one. I think there's still nobody here to come after me. I think I can answer one more while we are setting up. Feel free to.
So my question is definitely a great resource for this community. Do you have any idea of use of Wiki Data outside the semantic web community, or are you foreseeing any effort in advertising?
Yeah, mostly.
Outside?
I mean, to be honest, most users are outside the semantic web community. I'm here for advertising. I mean, I'm mostly here to tell you people to use it as well. I mean, we have, for example, Siri is using Wiki Data, and Google is using Wiki Data, yes. So mostly we see adoption in communities who are not semantic web, which was surprising to us. So because it's now 6 years since Wiki Data has been launched, and so far the uptake here in this particular community academically was not so big. So this year I've heard a lot of Wiki Data in the talks, so I hope this changes. But so far I think mostly people who don't care at all about semantic web are using it. And also the decision for RDF and BlazeGraph and Sparkle was not done because we are semantic web people. It was done by the foundation based on a review of graph databases, including some which are not based on RDF. And they just came to the conclusion it's the best technology for their use. So, yeah.
Thank you. Okay, so my talk has the title as mentioned. Subtitle is How Our Research Flew an Airbus Aircraft Simulator, only with semantic technologies. So you may be curious to find out how that works. So the motivation is that we have fine granular distributed components recently everywhere. So we have the Web of Things where we have interfaces to IoT sensors and actuators built on linked data. We have, for integration then, we have Solid that decentralizes personal data using the linked data technologies. Also, we have the trend to make to take software monoliths and subdivide them into smaller pieces and to run them individually. And the glue between that is mostly built on REST interfaces, which can easily be lifted to provide RDF for linked data. So we have a nice playing field with a uniform interface of read-write linked data. We have REST as uniform interaction mechanism, and we have RDF as uniform data model. So how do we want to make use of that? How we create integrated applications? And there is one proposal in the literature that says, why not use workflows? And if we buy that, we need a solution that combines workflows, semantic reasoning to integrate all these components in this field of RESTful interaction. And in this talk, I'm going to present you our solution. That's called WILD for workflows and linked data. So back to flying planes. Previously, we had a project on ergonomic studies of aircraft cockpits in virtual reality. So we built read-write linked data access to a flight simulator, a VR engine, to physical buttons and switches, finger tracking, head tracking, everything you see here. And we integrated that with a product description of the parts in the aircraft, such that eventually we can answer questions like, select the push buttons in the VR that are involved in the upcoming steps of the currently running takeoff workflow, such that the ergonomics analyst can say, okay, the finger is now here, it goes to over there. There may be something that you shouldn't touch at all in between, so we better put it somewhere else. For that, you need that live access, and these studies are being done in virtual reality. Yeah, so we had the workflows modeled, And after the project, we were wondering, okay, can we turn this around and fly the aircraft using that descriptions? And yes, we can to some extent, of course, in a very controlled environment. And in this talk, I'm going to talk about the foundations, what you need in terms of dynamics for that. Good. Related work, some workflow languages. Because you see boxes and arrows all over the place. For instance, if you look at BPEL web services, the boxes are more or less functions that return some value, and the arrows denote dependencies and parameters that are being passed. If you have scientific workflows like Pegasus, then it's about automating command line applications that terminate, and then you can pass on the data. So the arrows are dependencies, and the boxes are the command line applications. If you have some pipeline processing, like Taverna supports it, also scientific workflows, you have streaming operators that run forever, but the arrows, they are streams of data that are being passed. You see different environments, different requirements. The question is, we are now in read-write link data, so what are our boxes and arrows? And I will tell you in a minute. So as a basis for that, so as I said, we are in read-write link data, but what's the formal foundation? We came up with a model of computation for read-write link data. So what we did, and we published that at the ELO workshop this year, we took actual state machines, model theoretic semantics of RDF graphs, semantics of RDF data sets, and the semantics of HTTP, and built ASM4LD from that as a model of computation that supports read-write link data with everything you want to have, like the usual stuff, but also that you can write to link data. It embraces reasoning, and it embraces link following, and it's a Turing-complete thing. How does it look like? There's a syntax in N3 with 4 language elements. You have RDF assertions, you have deductions for reasoning, you have HTTP interactions that are reading, and HTTP interactions that are writing. And this is then executed in a certain way that involves looping this whole process, just very briefly. And that's like the environment that we want to use to specify and execute and monitor workflows. So we want to have a workflow language. And to give, the workflow language shouldn't just be for modeling, but we want to have operational semantics that allows us for monitoring and execution. Good. So can't we just use a run-of-the-mill BPEL engine and something like that? The answer is no, because we want to have something streamlined. So you can hook up a reasoner and everything to a BPEL engine that gives you the data integration and so on. But that's not what we want to do, because then we can't reason over the workflow itself, because it's not in the same uniform data model. That wouldn't have us allowed to answer the queries that I was showing you before. So we want something integrated. So then we have to address the challenges that are posed by our particular environment. We are working on the open world assumption in contrast to the closed world assumption when we, because traditional workflow management systems are built on relational databases. Also, we don't work with events in our environment because we are in REST and we don't have that. So we need to address that. How do we do that? We define post conditions to find out that an activity has terminated, and we check whether this condition is fulfilled on the overall state, for instance, of the aircraft or whatever your system is. And we model the dependencies, like the arrows here, with a heavy use of RDF lists. And that's how, because this is closed, we get around the open world assumption to find out whether something has actually finished. So this is the overall system setup. So here we have the engine, the rule engine that has the operational semantics of the workflow language and some OLLD reasoning semantics. And here the loop is happening over a set of linked data sources. So we model, the workflow model is in our vocabulary. We have workflow instances also modeled in a vocabulary. These are, of course, in a writable linked data platform container, because as we go, some activities finish and so on and so forth, and others become active. So this is like the approach that I'm presenting you today. Eventually, of course, we have a system under observation and control, like our flight simulation environment or your IoT devices. And they are accessed in the same uniform manner, such that we can reason over the whole thing using one system. So a quick look at the ontology. We have workflow models and instances. Here we have HTTP requests assigned to the activities if you want to execute something. And here are the post conditions. How does it work? We use that to describe the workflows. And here from the instances, we have pointers to the workflow models. Very briefly, this is how such a rule looks like. So we have a workflow instance that is active, and I want to show you how we activate the first activity in an instance in a sequence. We have an active workflow instance. It is a sequential thing. The thing is active, and we have an initialized first activity. And what we do, and there's a request assigned, and what we do is then we do a put request, set this first activity instance to active, and execute the corresponding request. And this is how we go. There are plenty of rules for that in the paper. Good. For evaluation, we formally aligned this with the workflow patterns. They are given in Petri nets, and we provided an argument how our operational semantics aligns to the semantics provided by the paper on workflow patterns. Like here you see we have a sequence, means that if there's the transition ends, the token is being passed to the next place. And similarly, our operational semantics performs the execution. And we do that analogously for the other basic workflow patterns. We also did a performance experiment. For that, we simulated a research building of IBM Dublin. There's a description provided in the brick ontology. And so we have a setup where we can automate things in the building, meaning that there are light switches and so on, and we can turn on lights depending on, for instance, whether the sun is shining or not. We did 5 automation workflows. They were as determined by a person for just representative workflows as you find them in the wild. He came up with 5 based on some clustering, and we run that on the different number of buildings. And if you know how these workflows work, you see like linear behavior in the complexity of the workflows and the number of buildings. If you zoom out a bit, what is the application scenario for this, what I presented you today? So you have decentralized components with read-write-link data interfaces. You have some need for data integration, otherwise you wouldn't probably use a reasoner in between. And you have some complex control schemes. So you want to go beyond rule-based control and have some notion of application state that requires a workflow to run. The layer cake, so to say, because in the semantic web community we were very fond of layer cakes. That's what I presented you today, workflows and linked data based on this model of computation for read-write-link data. If you want to align that with the semantic web layer cake, you have URI, RDF, and here we are in RDFS OWL because we use some transitive properties which are not in RDFS. If you zoom out even more and look at old artificial intelligence books, then because people are very curious about agents on the web, so with ASM4LD, we somehow, it roughly corresponds to simple reflex agents in Russell Norwick's books. Here we have some agents with internal state because the internal state is given by the workflow instance state. And this can then in turn be used if there's a planning agent to materialize out the result of his planning and to go for execution then. Good, thank you. That was my talk. I showed you an approach to combine REST semantics and workflows with an ontology and operational semantics. The main challenges were the open world assumption, which I addressed by RDF lists, and the lack of events, which we covered by using post conditions for the activities to know when they're terminated. Showed you some evaluation, some application scenarios, and then I would like to conclude my talk and see you at my demo tonight if you have any more questions. Thank you.
Hello, Patrick Semantic, Technical University. My question basically is whether you have somehow explored the relationship of this decentralized model to, for example, Sparkle Motion, all the solutions that are for pipelining of RDF.
Can you repeat?
Yeah, for example, there are solutions which are centralized, like Sparkle Motion for pipelining of RDF, creating RDF pipelines. So whether you have somehow explored the relationship between this solution and the other.
Pipelines for Sparkle processing.
Yeah, right. There are several ETL tools which basically do it on the centralized level, but this is another, of course,
so what
dimension.
we have here is decentralized components. So we tap the systems directly. But because we want to have a approach that is very broadly applicable, we take the minimum assumptions about the system, and the minimum assumption for us is RESTful interface and no streams. That's why, I mean, you could get in events through the backdoor with WebSockets, but that only applies to then a handful of your sources. And what do you do with the other ones? So that was the idea behind why we stuck to RESTful interaction. So that would be the connection to some streaming approaches that you may have in mind, but I'm not entirely familiar with that.
Okay, that's fine.
I have a short question about the relation to RESTdesk and
Yes.
How much reasoning do you have in the computation of the workflow? Because the workflow is kind of an imperative way of saying what to do.
Yes.
Where's the reasoning in there, and
Yeah.
do you compare to RESTdesk?
Okay, so it's two questions. Where's the reasoning and what is RESTdesk? Where's the reasoning? We have, in the ontology, we have some transitive properties, for instance, that we need to find out about the state of the workflow. Also, this running on a reasoner, all the data of the individual system can be integrated using reasoning, and you don't need to hook up an extra reasoner for that. So it leaves the place for reasoning in this overall setup, and there are tiny bits of reasoning to glue all these workflow bits and pieces together. Second, on RESTdesk. RESTdesk it's a description of, RESTdesk describes functions, and then they use a planning mechanism to find out how to get to some sort of goal. They only do one request at a time, and if you want to have some system state encoded in that, you have to get that in through the backdoor. Here, the system state, like the workflow instance state, is native. But if you want to have some state in RESTdesk, it's not very formalized also, but people have squeezed in system states through the backdoor as some kind of graph, and then you have started at zero.
But in the scenario presented with the building,
yes,
the agent is not one of the link data servers, right? There is an agent that navigates through all the servers and change their states to achieve a certain goal, right? It's not like it's not a multi-agent system.
Well, when you have one workflow, you have one agent, and if the agents themselves exhibit some sort of behavior, your post conditions need to cater for that. So we were studying pilots. So we have one agent that is the tracking system, and the other thing is the pilot. So we have two agents in the system and one tracks the other. So here are two agents. So we can cater for stuff that's acting if the modeling can cater for that, but there's room for that.
Okay, thank you.
Thank you. Let's thank the speaker.
Thanks.
That's fine. It's okay. You got it right.
In retaliation. And Alexander
Oh, just quickly see. Oh, okay. Do you want to use this, the keyboard?
Okay. Can you hear me? Everything okay? No? Is it better? Okay. So good afternoon, everyone. So I'm Alex Birko, and with Tivian Tanapalassingam, we're going to present you a smart book recommender. So it's ontology-based recommendation of editorial products, and it's done together by Open University, who does the real work, and Springer Nature, who provides the business use case. SKM3 group at Open University, they collaborate with us for quite some time, since 2014, and they have huge expertise in using data mining, semantic technologies, visual data analytics, and we are applying this together for scholarly data. In our cooperation, we already produced a number of things like Clink algorithm, computer science ontology, which is presented later, or like it's presented tomorrow, I guess. Tool for classification of 800 conference proceedings per year. It was presented at last ISWC. And also we have developed ontology evolution approach for pragmatic ontology evolution for different taxonomies we use inside Springer Nature. So how you evolve, for instance, subject taxonomy, making sure you take into account new topics but don't grow it too much. And we are using those technologies for practical problems. And this particular problem stems from the fact that we have a lot of books. Like computer science is a growing topic. Just in computer science, we have almost 15,000 books, a lot of conference proceedings, journals. And when you go to a conference, and the normal Springer editor goes to like at least a dozen of conferences per year, you need to understand what kind of books to bring. And you have certain criteria. You don't want to have very old books because the field grows, topics become outdated, and so on. You also want still to use maybe classical textbooks, books by keynote speakers. And you need to apply this kind of algorithms and selection for roughly a couple of hundred conferences per year. Of course, in the best case scenario, you are an editor who runs a program in, let's say, semantic web domain, and you have been doing it since like 15 years. So you know everything. There are no other people who publish stuff on semantic web, so you just bring your books and don't need to ask anyone. But in real life, of course, things are different. Maybe you are a guy who we just hired, you have no idea what was published before, and you need to browse through this like 13,000 books. And you also have other colleagues who may be published in this scenario. And I remember, like, a personal experience. For instance, I was going to another semantic web conference once, and I realized that Jim Handler published a book with our social science colleagues. How would you know this? So we need browse through large catalogs of information. You are resorted to kind of like normal text-based search, which is not very efficient. And in this work, we wanted to provide a more effective way to support this book selection process, to make sure you take the most interesting and most relevant books so that people can browse and authors of the books are happy. You don't need to involve too much your colleagues, so drive operating costs down and do it in a semi-automatic manner.
Thank you, Alex. So to solve the problem, what we have done is we designed an ontology-based book recommender system.
Please use the microphone.
I am using it. Is that not close enough? How about now? Yeah, much better? Okay. The approach is quite simple, so quite straightforward. We start off by building semantic representations of conferences. Sorry, okay.
Maybe you can use this one.
How about now? Sorry about that. I had a cold last week, so. So the approach is quite straightforward. We start off by building semantic representations of conferences and editorial products using a computer science ontology. And then we produce a set of books that have similar topic distributions to that of the input conference. Finally, and most importantly, what we do is we explain the user why we recommend certain editorial products. And we do this by visualizing the topic taxonomies of both the input conference and the suggested editorial product. One of the most important knowledge base that we are using for our system is a computer science ontology. Our ontology was automatically generated using an ontology learning algorithm called Cling2. It was presented at ISWC 3 years ago, so I'm not going to talk about it a lot. But it's worth mentioning that, we regularly update our ontology by rerunning the algorithm on updated web data sources. With around 14,000 research topics, our computer science ontology is the largest ontology in the field of computer science. It is accessible through a portal. The link is on the slide. There will be a talk tomorrow in this building at 2:20. I highly encourage everyone to go along to the talk because the talk will outline how you can browse our ontology and use it for your own project and contribute to our project by helping us fill in the gaps and make the world a better place for researchers. We start off by doing topic characterizations of books and conferences. We do this using a tool that we've designed called the Smart Topic API. And what it basically does is it maps metadata of papers and chapters to concepts in our ontology. And as a result of this process, we retrieve for each editorial product a set of research topics and the number of papers and chapters that mention that particular research topics. The benefit of this approach, to explain the benefits of this approach, let's consider these two abstracts from two different papers. The one on the left talks about ontology mapping. The one on the right talks about ontology alignment. If we use a syntactic approach, these would be classed as two different concepts. However, using our method, we're able to see that they both refer to the same concept. And we are also able to see that a paper about ontology alignment and or ontology mapping is similar to a paper about ontology or semantic web. And then what we do is we compute similarities between conferences and editorial products. We do this using cosine similarities and the research topics and their weights. Obviously, computing the cosine similarities for every conference and every editorial product is computationally expensive and can be very time-consuming. So in order to avoid doing that, what we do is we compute the Jacquard index, and our analysis has revealed that anything that yields a Jacquard index value of 0.25 or less produces unhelpful results. So we only compute cosine similarities on anything that's higher than that value. Finally, what we do is we have our application that we have designed. It makes multiple AJAX queries to our knowledge base and retrieves the data and displays the book recommendations. It also produces interactive visualizations in real time using D3 JS, which you will see later. When we started this project, we set ourselves a number of criteria. And importantly, we just wanted to keep things very intuitive and very minimalistic. That's why we gave the SmartBook Recommender a simple layout where at the top of the application, the user has a number of facets to customize their search, and at the bottom of the page, they have the book recommendations. By the way, I'm going to give you guys a small demo of the application. There's the URL. If you guys have internet connections, please try out the application. If you don't, you can come along to our demo session this afternoon. This is our booth, and try the local version of the application. So to search for book recommendations, a publishing editor can type in either the full name of the conference or its acronym. In this case, it's ISWC. You can see that the facets have been configured to search for books that have been published in the last 3 years. So as the user scrolls further down the page, they would be able to see the book recommendations in descending order of similarity. We try to provide all of the information inside the SmartBook Recommender, but we don't want to obviously overload the interface. So should the editor need more information about a specific editorial product, we do provide the link to the external sources like Springer Link and Springer.com. And we encourage editors to provide us feedback about specific recommendations. And as they give us feedback, we create a customized list for them that they can export out of our application and use it somewhere else. Lastly, but most importantly, we visualize the topic taxonomies of both the conference and the suggested editorial product, what they both have in common, and all of the topics that they both cover. And this is to kind of intuitively explain them why we have recommended the editorial product for this specific conference. What we have also done is we have done a user evaluation that involved 7 Springer Nature editors and 7 researchers. The main aim of this evaluation study was to see how good, how easy the SmartBook Recommender is to use and assess its quality of the recommendations. To this end, the user evaluation was carried out in 3 different phases. First, we introduced each subject to the SmartBook Recommender, and then we asked each subject to try out the SmartBook Recommender and rate each recommendations using one of the 4 categories: bring it or read it if they really like the recommendation, relevant if it is relevant to the conference, debatable when it's really hard to tell whether it's relevant or not, and irrelevant when it's completely irrelevant to the conference and shouldn't be in the list at all. And finally, what we did was we asked our subjects to fill in a questionnaire to tell us about their experience with the SmartBook Recommender. This slide summarizes our quantitative evaluation results. In the graph, you can see how each of our users evaluated by the researchers. We are working on improving these numbers. We also did a system usability scale test, which looked at how easy the application is to use. Again, the graph...
Applications are only available for conference which publish proceedings with Springer, because otherwise we don't have data. It's also only limited for computer science domain, but we see it more like a way we started with computer science domain and then we'll go further. And if there are books, like for instance, sometimes there are textbooks or monographs which have very few chapters, then the space of topics is quite sparse, so it's hard to consider like meaningful recommendations, and we hope to resolve this problem by considering full texts. We also want to make sure everyone in all continents in Springer Nature offices uses this tool in computer science, and want to experiment if adding data about sales, citation, altmetrics helps us create better recommendations. There is also in parallel work done on improving computer science ontology and extending it to other domains like engineering, for instance. And I would like to thank you on our behalf. Here are the key references for our work. Remember to visit our demo in the evening, and we are happy to take your questions.
So very nice work. I was wondering if you can add something more about the more qualitative feedbacks that you collected from Springer Nature editors on the tool rather than more the quantitative that you showed.
In terms of qualitative results, there were, our application was scored really high on the SUS score, and there were things that they suggested that we can improve to enhance the user experience, like it's a single page vertical application, and they were tired of constantly scrolling up and down, so installing these. And when the version of the Smart Book Recommender that we used for the evaluation didn't have the customized export option, so once you get the list, you download everything, and this was one of the ideas that I got from the qualitative results that they gave me.
So they were generally happy with that? They see that the tool is going to fulfill their own requirements?
Yes, and there are some certain improvements that we are still working on, customizing recommendations. And I don't see it as a tool that fully automates the book selection process. I see it more like a tool that supports it, at least kind of for the near future. And as time goes on,
thank you.
Things will get better. Thank you.
I probably missed some parts of your slides, but for Springer Nature, is it specialized for natural science or computer science? Because I saw that the ontology is about computer science. Then what about the other fields, basically?
Sorry, can you repeat that question again?
Because your ontology is about computer science, but what will happen to other fields if you don't have the ontologies, for example?
Sure.
Yeah, so essentially the process of selecting books is similar. Therefore, we think that if we expand ontology to topics beyond computer science, then we can reuse it in other editorials. As I told, the ontology extension to other disciplines is a parallel work, and basically once it's done, we probably need to do some evaluation of the tool with other departments, but after a couple of extensions, I think it will be scalable to any topic.
Sure.
Do you actually rely on metadata, or do you actually figure out from unstructured text what
No,
potential
we rely on metadata. I didn't work on this, I'm sure Francesca can do a better job.
I can fill in. Basically what we do is we rely both on metadata, such as title, abstract, and so on, keywords, but also we look at external knowledge, so call for paper, and for example, Wikipedia. And the idea is